Oh boy, it's another science video. How's it going, Science 10s? Today we're going to be learning about balancing chemical reactions. And balancing chemical reactions is fairly straightforward, but it requires a little bit of effort, and you just have to get used to a procedure. If it doesn't work the first time, then just keep trying. Maybe try it all over again, and eventually you'll be able to pick up what's going on. So in order to figure out how to balance a chemical reaction, what we have to do is we have to talk about a skeleton reaction or a skeleton equation. Now, skeleton equations are when chemicals react, the atoms and ions in those chemicals rearrange the way they are connected. Because matter can't be created or destroyed, this means that the number of atoms in each element must be the same before a reaction and after a reaction. A skeleton equation does not follow the law of conservation of mass. What that means is if we take this equation here, we're going to take a look at how many atoms of each element are in the reactants, and then we're going to compare that to how many atoms of each element are in the products. So let's take a look at the reactants. Where are the reactants? Well, the reactants are right here. So these are the reactants, and then these are the products. So let's take a look at the reactants. How many aluminums are in the reactants? Well, I see 2 aluminums. So we've got 2 times Al, 2 aluminums in the reactants. And how many sulfurs are in the reactants? Well, I see 3 are in the reactants, so 3 sulfurs are in the reactants. Now, according to the law of conservation of mass, if we start with 2 aluminums, we have to finish with 2 aluminums. We've got 2 aluminum atoms here, and when I look at the products, I do not see 2 aluminum atoms here. That's because this is a skeleton equation. So I only see 1 aluminium, and if we look at how many sulfurs are here, I see 8 sulfurs. So this doesn't work. This doesn't help us. When we look at this, there's no way that this is going to be able to work. This doesn't follow the law of conservation of mass. So what we have to do is we have to change this up a little bit. Now let's take a look at a properly balanced chemical reaction. In the balanced chemical reaction, we use coefficients. Now coefficients are numbers that are placed in front of each substance to indicate the quantity of each substance required to complete the reaction. Well, all that means is that we're going to place numbers in front of each substance, like for example here and here, in order to make sure that the number of atoms in the reactants is equal to the number of atoms in the products. So what we're going to do is we're going to split this up between reactants and products. So here we've got reactants on one side and we've got products on the other. And let's figure out how many of each there are in this chemical reaction. Well, I see here carbon, and there's no carbons over here, so there's just 1 carbon. I see 4 hydrogens, and there's no other hydrogens over here, so 4 hydrogens. And I see 2 groups of 2. So when we do this, 2 times 2 is 4 oxygens. Let's just take a look at the picture. Here, yeah, I see 1 carbon. The carbon is the black sphere in the middle. That's that black atom in the middle. So we've got 1 carbon. We see 4 hydrogens attached to it. One's hard to see, it's way on the back. And I see 2 O2s, 1 O2 here and 1 O2 here. So that's 4 oxygen atoms in total. Now when we compare that to the products, let's take a look at the products over here. We've got 1 carbon atom in the middle with 2 oxygen atoms to the side, and that's what's being represented in our chemical equation, CO2. We just got 1 CO2. So there's 1 carbon, there's 2 oxygens here, but then there's also 2 oxygens here. I see an oxygen in red there and another oxygen in red there. So there's 2 plus 2, or 2 plus 2 is 4 oxygens. And then we take a look at the number of hydrogens, and I see, yep, 2 times 2 again, so that's 4 hydrogens. Well, yeah, is this a balanced chemical reaction? It sure is. Does it follow the law of conservation of mass? Well, let's see. We've got 1 carbon in the beginning in our reactants, and we finish with 1 carbon in our products. That's good. That's what we should see. The atoms are just rearranging themselves. That's all they're doing. We've got 4 hydrogens in our reactants, and we see we've got 4 hydrogen atoms in our products. That's good. If you start with 4 hydrogens, you should finish with 4 hydrogens. And we've got 4 oxygens at the beginning before we react, and we've got 4 oxygens at the end after we've reacted. So yeah, the number of atoms and the type of atoms in our reactants is the same as what's in our products. This is a balanced chemical reaction. So what we're going to have to do is we're going to have to go back and we're going to have to place coefficients in front of all of our substances. When we place coefficients, or the numbers, in front of our substances, then that'll allow us to be able to follow the law of conservation of mass. So what we're going to try and do is we're going to try and balance a couple chemical reactions. So in order to balance a skeleton equation, we need to place the lowest combination of coefficients in front of each substance in order to make the number of each element equal in both the products and the reactants. So remember what we want to do. We want to have the number of aluminums at the beginning. We want that to be the same as the number of aluminums at the end, or in the reactants and in the products. Some basic principles that we want to keep in mind. Try to start with the most complicated element. Finish with the least complicated element. Okay, so let's just do equation number 1. I know we haven't talked about number 2, but whatever, that's fine. So let's do equation number 1. When I look at this chemical reaction, I only see 2 elements. I see aluminums and I see sulfurs. I see aluminums and I see sulfurs. So which one is the most complicated and which one is the least complicated? Well, I'm either going to start with aluminums or I'm going to start with sulfurs. I see that there's 2 aluminums over here, and here there's only 1 aluminum. So that seems pretty simple. Here, that seems pretty simple. There's just 1 of them, so that aluminums, they can be any number. If I toss any number in front, I can make any number that I want. Sulfurs, however, when I look over here, S8. That means if I leave it blank in front, that's a 1. So 1 times 8 is 8 sulfurs. If I put a 2 in front, that means 2 times 8 is 16 sulfurs. So I can only use groups of 8 sulfurs. That seems pretty complicated. I'm going to start with the most complicated element, which is sulfur, and I'm going to finish with the least complicated element. Okay, let's try this out. So let's look at sulfurs. At the beginning and at the end, in the reactants and in the products, I see 3 sulfurs in the beginning and I see 8 sulfurs in the end. Well, can I turn groups of 3 into groups of 8? So if I add a 1, 1 times 3 would be 3. That doesn't work. 2 times 3 would be 6. That doesn't work. 3, if I put a 3 in front of this, 3 times 3 is 9. No, I can't make a group of 8. Okay, well, let's see what groups I can make. 3, 6, 9, 12, 15, 18, 21, 24, and I'm running out of room. Okay, sure. Let's see what groups we can make with 8. 8, 16, 24. And hopefully you'll see that 24 is my lowest common multiple. And we've talked about the lowest common multiple before. So we're going to use our lowest common multiple to be able to figure out how many of sulfur atoms we need. Well, I know that I can make 24 out of groups of 3, and I know I can make 24 out of groups of 8. So let's use those numbers. So what I'm going to do is I'm going to toss an 8 in front of here, because 8 times 3 is 24. Now I'm not going to toss 24 in front of here, because that 24 times 8, that's insane. That's not going to happen. That's 192. But what I can do is I can toss a 3 in front of here. 3 times 8 is 24. So we've got 24 sulfurs and 24 sulfurs. Now, by putting an 8 in front of this compound, I not only change the number of sulfurs, but I also change the number of aluminiums. So now we don't have 2 aluminiums anymore. We have 16. 8 times 2 is 16. So let's go back over here and let's see if we can make 16. Well, this is easy. This is 1 aluminium, or aluminum, and if I have 16 groups of 1, then that's 16. So let's just double check. 8 times 2 is 16 aluminiums. 16 times 1 is 16 aluminiums. Good. 8 times 3 is 24 sulfurs. 3 times 8 is 24 sulfurs. Perfect. So this is a balanced chemical reaction. This works. Our coefficients are 8, 16, and 3. Let's try another one. We're going to have to use a different principle or a different rule this time. So the principle that we're going to have to use this time is the idea of treating polyatomic ions as one element, as long as they stay together, as long as they don't change. So when we take a look at this first compound here, okay, it's an ionic compound. It begins with a metal. Sure, it's an ionic compound. And so this is silver perchlorate. Hopefully you should recognize perchlorate is here, but also perchlorate is here. Phosphate, PO4, is here, and PO4 phosphate is here as well. And I'll do that in a different color. So the phosphates are blue, the phosphates are blue. So we can still use our first principle, what's the most complicated compound or element, but they all look pretty darn complicated. It doesn't matter to me. So I don't know. I'm just going to go off of kind of what I feel. It looks like the second one is more complicated than the first one, because this is Ag1ClO4 and this is Na3PO4. So I'm going to start with this one. Sure. So start at the beginning. We've got 3 sodiums. So I look to the other side of the equation and I see, okay, we've got 1 sodium. 3 sodiums over here and 1 sodium over here. So I have to place a 3 in front. No problem. Now by me placing a 3 in front of this compound, there's 3 sodiums, but now there's 3 perchlorates. You just deal with the ClO4 as one unit. How many perchlorates, how many ClO4s are here? There's not 4. We don't have 4 perchlorates. There's 4 oxygens in 1 perchlorate. So there's 1 perchlorate, but now 3 times 1 means there's 3 perchlorates. So I'll go back to the other side. I see 1 perchlorate, 1 ClO4. There's not 4 of them, there's 1 ClO4. So if I want 3 perchlorates, I say 3 perchlorates. Now there's 3 silvers, so I go to the other side. There's 3 silvers. There's 1 phosphate, 1 PO4, 1 PO4, 3 sodiums, 3 sodiums. We're balanced. Everything here is perfect. Let's just double check, just because we want to double check, sorry. 3 silvers on this side. 3 perchlorates on this side. 3 sodiums on this side, and 1 phosphate. 1 PO4 phosphate. Let's take a look at the other side. We've compared all the reactants now. Now we got to look at the products. There's 3 times 1 is, so 3 sodiums. That's good. 3 ClO4s. So there's 3 perchlorates. There's 3 silvers. And there's 1 phosphate. So yeah, this is perfect. We've got one phosphate, one phosphate, 3 sodiums, 3 sodiums, 3 perchlorates, 3 perchlorates, 3 silvers, 3 silvers. Everything is perfectly balanced. And this was made a lot simpler because we treated polyatomic ions just as one element, and we just balanced that one element. So now what we want to do is we just want to do some practice, and you might have already had this sheet, you might have already filled it out in class, but we're going to do a couple problems about this, and I'm going to show you how simple this can be as long as you're following the rules. So let's take a look at the very first one. Let's do the first problem. So we're going to take a look at the simplest element, and we're going to do that last. We're going to do the most complicated element first. So I see sodium with a 1 after it. It's invisible, we don't write it, but it's implied that there's a 1 there. That's obviously the simplest element. O2 is the most complicated element. So I'm going to start with oxygens first. I see we're always looking at the reactants and the products separately from each other. So I've got 2 oxygens on the reactant side. I've got 1 oxygen on the product side. So if I want 2 on both sides, I'll put a 2 here. Now, by me putting a 2, I've changed the number of sodiums. So now there's 2 times 2 is 4. So there's 4 sodiums here. I got to put a 4 here. And those are the coefficients. The coefficient here is 4. The coefficient here is 1, but we leave it blank. We just leave it blank, and it's implied that you're only going to use 1 of them. And then there's 2 sodium oxides. Okay, perfect. Let's try another one. Another one that'll be a little bit more complicated. We're going to go all the way down to G. So let's do G. So I look through here and I see, okay, what's the most complicated element? What's the simplest element? Well, I see, okay, you got borons, nitrogens, and chlorines. Chlorine looks the most complicated over on this side. Borons, nitrogens, and chlorines, borons, chlorines, and nitrogens. And chlorine is still the most complicated. It's got kind of the highest number attached to it. So let's do chlorines first, and let's just see where that takes us. So if I've got 2 chlorines over here and 3 chlorines over here, well, 2 and 3, the lowest common multiple between those, 2 can make 2, 4, 6, 8, 10, and 3 can make 3, 6, 9, 12. So 6 is the lowest common multiple. We want to have 6 of each. So the only way I can have 6 chlorines here is by throwing a 3 in front. The only way I can have 6 chlorines here is by throwing a 2 in front. Well, what did that change? The number over here didn't change any other element, but this coefficient over here, 2 borons now. So we have 2 borons. Well, that changed the number of nitrogens as well, 2 nitrogens. But I look over here and there's already 2 nitrogens. Perfect. We are balanced. 2 borons, 2 borons, 2 nitrogens, 2 nitrogens, 6 chlorines, 6 chlorines. No problem. We're going to do one last problem, and just try these balancing chemical reactions. Just try them out yourself if you haven't already done it in your notes. So let's take a look down at one of the really complicated ionic compounds, and some of my problems are kind of peeking out here, so I'm just going to move over. We're going to do K. This one is K, and we're going to do K. So let's take a look at it. It's really tough for people to identify polyatomic ions when you've just learned about them a couple weeks ago. But let's take a look at it. These are all ionic compounds, and they look pretty complicated too. This is lead something. This is potassium something. Everything here is a polyatomic ion. Hopefully you notice Cr2O7 doesn't change. Cr2O7, that doesn't change. And that's because it's a polyatomic ion. It's called dichromate. So let's treat it as if it's just one thing. So what's the most complicated thing in here? I don't know. Maybe the lead is the most complicated. I have no clue. So let's go through this. Maybe the first one is the most complicated. It's either the first one or the third one. But let's just do the first one, whatever. So 1 lead, 1 lead. I don't have to do anything there yet. 4 NO3s, 4 nitrates. So I see we've got 1 nitrate here, so I'm going to put a 4 in front of it. Well, what's that changed? That's changed the number of potassiums. So I need 4 here. They come in groups of 2, so I'm going to go 2 times 2 is 4. Well, what did that change? That changed the number of dichromates, Cr2O7s. I have 2 Cr2O7s. Well, over here I've got 2 Cr2O7s. We're balanced. This is a perfectly balanced reaction. So if you have any questions, let me know. Just try these examples, and I'll put the key on Google Classroom, or I'll put the key in the schedule, and let me know. Talk to me during my office hours. Let me know if you have any questions. Thanks a lot, Science 10s. I'll see you later.